All right, let's jump right in. Welcome to an epic explainer where we're going to explore the absolutely mind-blowing scale of life's resilience. We are taking a trip through deep time today, journeying from ancient, microscopic catastrophes all the way to the ultimate cosmic destiny of our planet. You know, when we look at Earth's history, it's super easy to think of life as fragile. But as we'll see, the reality is a story of brutal survival and just awe-inspiring adaptation.
Here's our roadmap for today's journey. We'll start with the oxygen awakening, meet some prehistoric giants, witness the Jurassic rebirth, explore the insect social revolution, and finally, look way ahead to Earth's final destiny.
So part 1, the oxygen awakening, or Earth's first apocalypse.
We're actually going to start super small, microscopic in fact, with an event that proves the very air we breathe right now was once a devastating weapon. Around 2.4 billion years ago, these tiny organisms called cyanobacteria figured out a brand new trick, photosynthesis. But in doing so, they completely accidentally triggered a 300 million year global deep freeze known as Snowball Earth. How? Well, by flooding the atmosphere with a byproduct that was a literal, deadly poison to almost all other life at the time: oxygen.
It's crazy to think about, but life's worst climate crisis actually turned into its biggest lucky break. See, that newly unleashed oxygen violently reacted with atmospheric methane, which was a super potent greenhouse gas, keeping the early Earth nice and warm. With the methane gone, the planet froze solid into a global snowball. Life had to run for cover, retreating into thermal refuges deep under the ice or clustered around marine volcanoes. But when the ice finally melted, all that accumulated oxygen had built the ozone layer, which shielded the surface from deadly solar radiation. Out of that apocalyptic freeze, complex nucleated cells, eukaryotes, were born. And those are the ancestors of all modern plants, animals, and fungi.
Moving on to part 2, prehistoric monsters and giants, and the extreme scale of life.
Let's fast forward a bit to the Carboniferous period, about 300 million years ago. That exact same oxygen we just talked about, well, it ended up fueling biological extremes that we can barely comprehend today. Just compare our current atmosphere, which sits at roughly 21% oxygen, to the prehistoric air, which was a massive 35%. That huge difference completely explains how insects were able to become massive without changing their fundamental anatomy.
So why does that 35% matter so much? Because insects don't actually have lungs like we do. They breathe passively through a network of tiny microscopic tubes called trachea. In today's world, a giant insect would just suffocate because the oxygen simply couldn't diffuse deep enough into its massive body. But with that heavy 35% concentration back in the Carboniferous, the gas basically acted like a biological supercharger. This incredibly high-pressure oxygen environment is exactly what allowed for terrifyingly large bugs, like eagle-sized dragonflies called Meganeura and 2-meter-long centipedes known as Arthropleura.
Now, this brings us to a fascinating physics trap called the square-cubed law. Think of it like this. Insects basically wear their skeletons on the outside. It's fantastic armor, right? But it comes with a catch. If you scale an insect up, its weight multiplies way faster than its leg strength. Physically, it should just crush itself under its own weight. But that incredibly dense, ancient atmosphere actually helped compensate for the massive energy needed to lug that heavy armor around. Today's insects survived as those oxygen levels dropped simply by doing a 300% zoom out in size. It's proof that their core anatomical design is just practically indestructible.
All right, part 3, the Jurassic rebirth and bouncing back from extinction. We're jumping to 201 million years ago, where a massive volcanic extinction event basically wiped the slate clean all over again. Intense volcanic activity made the oceans highly acidic and choked the skies. And while incredibly tough survivors like the sturdy Lystrosaurus managed to hold on through those brutal times, the Earth itself was fundamentally broken. It took a staggering amount of time, we're talking up to 10 million years, to fully recover its complex interconnected ecosystems. So the big takeaway here is that this recovery was completely stepped. It definitely didn't happen overnight. For the first 500,000 years, only basic, opportunistic species survived. Then, around 2 million years in, the seas quickly filled with ammonites in this explosive evolutionary radiation. Between 3 and 5 million years, terrestrial dinosaurs rapidly stepped up to claim the ecological niches left totally empty by extinct giant amphibians. But the fragile coral reefs, they were so devastated by ocean acidification that it took them a full 10 million years to truly restabilize. And with the previous dominant predators out of the picture, dinosaurs underwent a monumental shift.
They evolved from these agile, small-scale hunters, much like the Coaphysis, into monumental living skyscrapers. The long-necked sauropods stretched upward to reach high tree canopies, taking full advantage of completely open biological playing field.
Meanwhile, down in the oceans, a total reinvention. Giant marine reptiles emerged to dominate the seas, including long-necked plesiosaurs and absolute behemoths like the ichthyotitan. It's just a profound demonstration of life's incredible capacity to scale up when given the room to grow.
Which brings us to part 4, the insect social revolution and the rise of the superorganism.
While literal giants were ruling the Jurassic and Cretaceous periods, another, arguably way more powerful revolution was brewing right underfoot. Insects were trading physical size for sheer collective intelligence. Around 100 million years ago, certain wasps transitioned from solitary hunters to complex eusocial colonies through a few very specific steps. First, they were just solitary parasitoids. Then, they began building these communal apartment nests right next to each other, mostly just as shared defense duties against predators. But eventually, a dominant alpha female emerged, suppressing the others and essentially forcing them to be her workers. And just like that, the colony as a single superorganism was born.
75%. That number right there is the absolute secret to their ultimate altruism. I mean, why on earth would a worker ant or bee give up her own life and her chance to reproduce just for the colony? Well, it's because of a strange genetic quirk called haplodiploidy. Ant and bee sisters actually share 75% of their genes with each other, but they'd only share 50% with their own offspring. So strictly from an evolutionary standpoint, it is mathematically smarter and technically more selfish for them to protect their sisters and the queen than to breed individually.
Now here's a wild twist. While ants and bees evolved from wasps to form these strict female matriarchies, they totally weren't the first to do it. Termites are actually highly evolved wood-eating cockroaches. They needed to stay together in close-knit families to share the intestinal microbes required to digest wood. Because of this, they established complex mixed-gender societies featuring both a king and a queen a full 30 million years earlier than ants or bees ever did.
Finally, we reach part 5, Earth's final destiny and the ticking cosmic clock. From the deeply organized metropolises of insect colonies and, our own human cities, we really have to look ahead to the inescapable, fiery end of our world. It's not going to be some sudden dramatic supernova that ends us. It's actually a slow mathematical certainty. The sun's radiation is steadily increasing by about 1% every 100 million years. Long before the sun ever becomes a red giant in 5 billion years, this creeping, increasing brightness is going to completely shatter our planetary ecosystem and simply boil our biosphere away.
The final days of our planet are basically already mapped out for us. In about 600 to 800 million years, that extrasolar heat is going to trap CO2 down in the soil. Without atmospheric CO2, photosynthesis just stops. Plants suffocate, and terrestrial food chains will immediately collapse. By the 1 billion year mark, the sun will be 10% brighter. Average global temperatures will hit roughly 47 degrees Celsius, triggering a runaway moist greenhouse effect that literally evaporates the oceans and extinguishes all complex life. And finally, around 2.8 billion years from now, temperatures will soar past 140 degrees Celsius. That is hot enough to physically destroy DNA, completely sterilizing the Earth and leaving it a dead world, much like Venus or Mars.
So as we step back and look at the immense resilience of life over billions of years, we're hit with the realization that our current habitable era is uniquely precious. But it's undeniably finite. The cosmic clock is ticking, and it leaves us with one incredibly provocative thought. Life has survived ice, volcanoes, and toxic air. But will our own species' collective intelligence and resilience be enough to take us to the stars before our time finally runs out?